So in the previous lecture, we understood about static and kinetic friction, and we understood that the static friction in general acts when there is no slipping, because the static frictional force is able to balance the tangential external force. Static friction balances the tangential force, okay, creating a tendency to slip. And as a result of that, the static frictional force acting on it is less than equal to coefficient of static friction into normal reaction. Whereas kinetic friction is the type of friction that acts when slipping is taking place. Okay, when the two surfaces are slipping with respect to each other, the kinetic friction equal to mu k into n. What it does is it opposes the slipping. Okay, so it does not have a variable magnitude. It does not adjust according to external force. In fact, it has nothing to do with tangential force. We saw last time that even if the slipping is occurring and tangential force is removed, but because of the momentum of the body, it continues to slip for some time. Even in that situation, kinetic friction will be acting, because after all, the two surfaces are in a process of slipping. So the friction immediately is acting opposing the slipping like that. Okay? And the magnitude of the kinetic frictional force acting then is independent of external force anything. It only depends on the nature of the surface and therefore the coefficient of friction, and of course the normal reaction. So these facts we've understood last time. Okay, now let's begin with some example questions today. So first thing is that let's look at a question where we understand the concept of net contact force as the vector sum of normal reaction and friction when both are acting. So suppose we have a situation like this. So this is now a surface which has a given coefficient of friction, or you can say a given set of coefficients of friction. So coefficient of static friction is, let us say, 0.5, and coefficient of kinetic friction is, let us say, 0.4, and this is a block of certain mass on which we are applying a certain amount of external force. So the block of m equal to 10 kg is initially at rest. So we have to find out the net contact force on the block, okay, due to the rough horizontal surface on which it is lying. Okay. And secondly, the angle made by this net contact force with respect to the vertical. So we have to find out these two things when F equal to, okay, so let us say a force of 40 newtons is applied, force of 60 newtons is applied. In both cases, F is applied horizontally as shown. Okay. So in this type of question, what we have to understand before we get into it is that what we mean by net contact force. What is the net contact force? It is the vector sum of normal reaction force, okay, and friction, okay, because both are contact forces. So the net contact force is the vector sum of these two. So just try this out now. So as usual, all you have to do is make the free body diagram in each of the cases and calculate how much normal reaction and how much friction is acting, and then just find out the this thing, the vector sum of normal reaction and friction. That will give you the net contact force. Okay, the concept is clear from what I'm saying. Okay, the net contact force is the vector sum of friction and normal reaction. So on a body which is sliding, suppose a body is sliding in this direction, if there is certain amount of friction acting, say kinetic friction in this case, okay, and certain amount of normal reaction, then the net contact force is the vector sum of these two things. Okay. They will always act perpendicular to each other. So this thing, this quantity over here, let's say this is some R or something. This R is the resultant sum of normal reaction and friction, and that is the net contact force. Okay. And this angle theta is the angle it is making with respect to the vertical. So in each of these situations A and B, you have to calculate what this R will be, this net contact force or resultant sum of the two forces, sum of the two contact forces. Yes, that's correct, Aman. You can give the answer in square root form also. You don't have to calculate the exact value. You can give the answer in square root form. That's fine. Yes, in the part, so I'll just put up the answers first. So in A part, the net contact force, okay, you can say R or whatever, it will be 20 square root of 29 newtons, and it will be at theta equal to tan inverse 0.4 with respect to vertical. Now, interestingly, in B part also it remains the same. Again, be same. Now let's understand why in each of the cases. So in case A, your free body diagram will look like this. You are applying a force horizontally of 40 newtons, whereas maximum static friction is equal to how much? It is 50 newtons. Therefore, acceleration of the block will be zero. The block will be at rest. So acceleration will be zero, and there will be static friction equal to F acting on it. Apart from this, of course, there are the okay. So normal reaction will be equal to mg, which will be 100 newtons, and static friction will balance the external force, so it will be 40 newtons. So as far as net contact force is concerned on the block, there is static friction of 40 and normal reaction of 100. So their vector sum, this becomes the resultant contact force. And this angle is theta. So you can see that this is the resultant force. And tan theta is nothing but 40 by 100. Okay. Now in the second case, in the B case, the situation of the block will be slightly different. It will start sliding. But interestingly, just by chance what is happening, because coefficient of kinetic friction is zero point 0.4, the frictional force acting, though now it will be kinetic friction, but it will be 40 newtons only. So there's no difference in the forces. There's only a difference in the state of the block. It will start accelerating horizontally because we have bumped up the value of F to 60 newtons or whatever, 50, more than 50 newtons. So it will start accelerating, but as it starts accelerating, this kinetic friction becomes, I mean, the friction becomes kinetic in nature. So it becomes mu k into n, and coefficient of kinetic friction I had given you in the question was 0 0.4. Okay, so this is what is happening in this case. So though it might seem a little odd, but it's just because the values are such over here. Both cases, the answer is the same for the resultant force and the angle. Snikita, hope you checked the answer. It's clear now. Okay. So this will be, by the way, approximately 107.7 newtons and zero point 0.4 tan inverse. Though actually we don't need the values like this. This is enough to give it in square root form. Okay. But just for your reference, this is about 21.8 degrees. Okay. So now hope all of you understood why the answer is going to be the same in the second case. Okay, because though the body is now sliding, okay, but the kinetic friction, because of the value of mu being zero point 0.4, mu k being zero point 0.4, it will be the same. It will be 40 newtons. So even when I've increased this force to 60 newtons, but because the coefficient of kinetic friction was zero point 0.4, okay, this is 40 newtons. So now the body is accelerating. Unlike the previous case, the body is accelerating. Okay, it will be 20 by 10 or whatever, 2 meters per second square. But that doesn't really matter for us over here because we are only interested in this, the vector sum of normal reaction, which is 100 newtons, and this time kinetic friction, but the value is the same, 40 newtons. It will be the same. So, theta is tan inverse 0.4 or 21.8. Is okay. Okay, now let us move on to a different type of question. Now all these questions that we are doing, they are sort of standard examples. So it's very important that you not only understand the question here, but just remember the process for solving them for other types of questions or other questions involving friction. So this time what is happening is we are given just one value of mu. So that is 0.4, let us say. Okay. So that means the coefficient of static friction is equal to the coefficient of kinetic friction, which is 0.4. We have to assume that. Okay. Now what is happening is that so the block is at rest initially. So m equal to 50 kg, g equal to 10 meters per second square. The block is at rest initially. Now what we're doing here is we are going to apply an external force, but we are not going to apply it horizontally. We're going to apply a force like this at an angle of theta to the horizontal. So what we'll do here is, if an external force is applied at theta, the external force F is applied at theta to the horizontal, then first of all find the minimum value of F, the minimum magnitude F needed to move the block, okay, as a function of theta. Okay, and calculate it for theta equal to 37 degrees, theta equal to 45 degrees. Okay. Now second part of the question is very interesting. Once we find this as a function of theta, we have to minimize this function, that is f as a function of theta, to find the minimum magnitude of this external force needed. Okay. And the angle theta at which it should be applied. So if I had the option of varying the angle at which I'm applying the force, then first of all, what angle I should apply the force at, so that I can move the block with minimum amount of force. And what is that minimum amount of force? So what is that minimum magnitude of force? Okay, so this is a more complex type of problem. Make the free body diagram for the first part and try to get f as a function of theta. Then you will automatically understand what the second part is trying to say. Okay, don't worry about the second part immediately. Just follow the instructions of the first part and try to get f as a function of theta. Then once you got f as a function of theta, read the second part of the question and you will understand what we mean by saying minimize the function, so that you can get the angle theta at which the force should be applied for it to be minimum. Okay. So there's a bit of application of maxima minima theory from calculus also over here. Okay, so let me work out the first part. So to get this mu as a function of theta, you make the free body diagram of the block. So when it's lying on this surface, now we are applying this force at an angle theta to the horizontal. And while we are doing that, there is mg acting, there is normal reaction acting, and there is friction acting. Okay. So we can resolve the forces and make the free body diagram like this, that F cos theta is acting horizontally, F sin theta and normal reaction are acting vertically, mg is acting vertically downwards, and friction is acting like this. Okay. So for the block to start moving, F cos theta should be greater than maximum friction. Okay. So F cos theta should be greater than, even just about equal to will be fine, mu into n. F cos theta equal to mu n is what we call the limiting condition. So the limiting condition means, okay, the block is just about ready to move under this. Okay. So now the other equation, of course, is that, so after resolving the forces, we have n plus f sine theta is equal to mg. So the normal reaction is mg minus f sine theta. So we have this equation and we have this equation. Now from this, to find the minimum value of f, we have to substitute the value of n here. So substitute normal reaction here. And this equation becomes f cos theta should be greater than equal to mu into mg minus f sine theta. That means f into cos theta plus mu sine theta should be greater than equal to mu mg. So that means f should be greater than equal to this thing. Okay. So this tells me that the minimum f needed to move the block, that is mu mg upon cos theta plus mu sin theta. This is the minimum force as a function of theta. So I'll just leave you with a moment to understand this equation, how it is coming from the free body diagram. Okay. And next then we will analyze this. Okay. So for the first E part, substitute theta as, what was it? 37 degrees. Yeah, 37 and 45. M, I think we are taken as 5 kgs, sorry, 50 kgs. It will be very close to 200 only. something like this. This will be the minimum. For the B part, theta equal to 45 degrees. So F minimum will become umg upon 1 by root 2 plus 0.4 by root 2. So you can write this as 200 root 2 upon 1.04. So this will become, sorry, upon 1.4, not 1.04. So you can approximate root 2 as 1.4. So this is approximately 200 only. So for theta equal to 45, you can see the minimum force required has changed quite a bit. If I'm applying the force at 45-degree angle, then the minimum force I need to apply is about 200 newtons. If I'm applying it at 37 degrees, then the minimum force I need to apply is less than that. It is about 192.31. Okay. You can see that if I apply it at different kind of angles, I require different amount of force to move the block. Yeah, Jewel, I think your answers are approximately correct. Now let's come to the second part. So you have understood this thing, I hope, that how we got the minimum force at any general angle theta as a function of theta. Now what we want to do, we want to minimize this function. Understanding? So that's the second part. So that's the more tricky part of the question. Okay. Because you're going to have to apply this thing now. Maxima minima concept. Greater than equal to is fine because just about equal to means the block starts to move. It has a tendency to just start moving at that value. Yeah, so you understood now, Snikita, why the free body diagram is ultimately very important. Otherwise, you'll miss out one component or the other. No? Okay, now let's come to the second part. So, at a general value of the angle theta, okay, the minimum force needed to move the block, F minimum, is given by this function mu mg upon cos theta plus mu sin theta. Okay. And we already saw examples of this. For example, at theta equal to 37 degrees, we saw the minimum force required is about 192.7 newtons. Okay. At theta equal to 45 degrees, the minimum force required was about 200 newtons. So now this has to be minimized. Now we want to find the value of theta for which this function f theta equal to mu mg upon cos theta plus mu sin theta. This whole function has a minimum. Okay. So that is basically what we are doing in the second part. We are free to select any theta we like. Now we want to select that value of theta so that we can move the block with minimum amount of effort. So that is this function f theta, which is the force required to move the block, that is minimized. Okay, hope you are understanding the point. ये एफ मिनिमम का मिनिमा निकालना है ना. एफ मिनिमम इज द मिनिमम फोर्स एट सम थीटा. नाउ व्हाट इज द मिनिमम वैल्यू ऑफ that limiting force we require if we keep selecting different values of theta? Like if we have adjusted 37 and 45, we've seen that out of these two we require less force in 37. But how do we know that if we go from 37 to 30, will the required force become even lesser or will it increase again? We don't know that, right? So we have to use maxima minima to understand that. Okay. So now for this, we will use a very simple concept. We won't actually use maxima minima. If you notice here, this thing, it is mu mg upon cos theta plus mu sine theta. So it is basically a constant, mu mg is a constant divided by a function of theta. Let's say that function I'm writing as g of theta instead of f of theta. So therefore you can see that f of theta is minimum when the denominator, that is g of theta, is maximum, because the numerator is a constant. So if I just maximize the denominator, okay, I can find out the minimum force required. So in other words, therefore, this functions, okay, now I want to find out the maxima of this function. What is the maximum of this? And this you should all know from trigonometry. आपको maxima minima use करने की जरूरत ही नहीं है यहाँ पे. It's a linear function in cos theta and sin theta. So what is the maximum value? Yes, very good, Kevin. That's correct. Square root of 1 plus mu square. Okay. So first of all, I want all of you to understand this thing over here. What we are trying to do in this part. Okay. We are trying to find the minima of the function f theta. So function f theta कब minimum होगा जब उसका denominator maximum होगा, because the numerator in that function is a constant. It's not varying with theta. You can see this function f theta, the numerator is constant, only the denominator is a variable quantity. So if I maximize the denominator, the numerator, the function itself automatically becomes minimum. Yeah, but plotting the graph itself which means that you have to know the minima. No? Without information about maximum minima, you cannot plot any graph. No? So you can just use the concept from this thing, from trigonometry, that this quantity's maxima is equal to square root of 1 plus mu square. Okay. And minima is of course 0. Okay. I mean, you can say minima is negative of 1 plus square root 1 plus mu square, but that is not relevant here and it's not important. Okay, let's just concentrate on this. So how do we know this? Okay, so that is where your trigonometry knowledge comes in. Okay, so I'll just give you aside something else. Okay, if we have a function y equal to a sin x plus b cos x, where a and b are constants, so it can be written as multiply divide by a square plus b square square root. Okay, so it is square root of a square plus b square, a upon square root of a square plus b square sin x plus. So this manipulation in trigonometry, trigonometric equations, this kind of manipulation, that whenever you have a linear function in sin x and cos x, to solve it, you actually multiply divide by root of a square plus b square, where a and b are the coefficients of sin x and cos x. Next step, you do this. Okay. Now in this step, what you do is, suppose this constant is cos of some alpha. So you can see automatically this constant becomes sine of that same alpha, because sine square alpha plus cos square alpha should be 1. And that will always be the case. So you can write this as root of e square plus b square into sin x cos alpha plus cos x sin alpha. So this becomes sine of x plus alpha. Okay. So you can see that y's maxima is equal to root of a square plus b square. Okay. And this occurs when sine of x plus alpha is pi by 2. That means x plus alpha is pi by 2 or 90 degrees. That means alpha is pi by 2 minus x. Okay. Now from here you can see that sine alpha was b upon root of a square plus b square. Cos alpha was a upon root of a square plus b square. Okay. So tan alpha is b by a. And from here, tan alpha is equal to cot x, or tan of pi by 2 minus x. So alpha is equal to pi by 2 minus x means that b by a is equal to tan pi by 2 minus x, or x is equal to pi by 2 minus of tan inverse b by a, or that is cot inverse b by a. Okay. So this trigonometric concept will apply over here. So यहाँ पे क्या आ रहा था देखो, this function was cos theta plus 0.4 sin theta. Okay. So this function's maxima will be square root of 1 plus 0.4 square. So square root of 1.16. Okay. This will be nearly 1.08. And it occurs, I mean, this maxima occurs for theta equal to cot inverse b by a, where b is the coefficient of cos and a is the coefficient of sine. So 1 upon zero point 0.4, or theta equal to cot inverse of 2.5. Okay. So once we have found this, now we will see that okay, the function f theta's minima was equal to mu mg divided by g theta's maximum. And what was g? This thing. This was zero point 0.4 into 500 divided by this maxima. Now this maxima's value is how much? Is this much? So we will see that this will come out to be approximately about 185 point 2 newtons. So this is the minimum force required to move the block. But this will be when we apply it at an angle of theta equal to cot inverse 2.5, or that is the same thing as tan inverse zero point 0.4. So that is approximately 21.8 degrees. So I'll also show you the calculus way, the differentiation maxima minima method of finding out this minima of the function. Okay, but this is the method that should strike you immediately, because you can see the denominator has a linear function of theta, linear function of cos theta and sin theta. So the moment you see anything which has a linear term in cos theta and sin theta, you should immediately know that okay, we can apply this trick, that a sin theta plus b cos theta can be reduced to square root of a square plus b square into sine of theta plus something. This is one of those general little tricks in maths that you can use number of places in physics. Whenever you see a linear function in sine and cos like this one, y equal to a sine x plus b cos x, you can reduce it to a single trigonometric term like this, that y is equal to square root of a square plus b square into sine of x plus alpha. So you just remember this trick. It's very very useful thing in physics. Okay, so hope you understood this method. Now, just as a quick alternative, the calculus method for maxima minimum, how we can make use of that. So this f minimum, which was expressed as a function of theta, was this. It was like, so now this function's maxima we want to find out. Okay. So what is the first step? You find derivative of this. That is, okay. Of course, in this also you can use the trick that first. Sorry, we wanted to find out minima of this. So you can use the same trick that you can find out the maxima for the denominator. Okay, but I'm saying even if you don't do that, you always have this option of differentiating this. So this is nothing but, okay. Uh, so numerator into differential of denominator minus denominator into differential of numerator divided by denominator square. So numerator's derivative is 0. So that's why this will become nothing but, or just apply the chain rule. So it is minus mu mg upon cos theta plus mu sin theta square into derivative of this. So that is minus sin theta plus mu cos theta. Okay. So this is the derivative of the function. This is the derivative. So now you apply the minima test. Okay. Test for minima. That is what we mean by local minima of the function. So derivative should be 0. Okay. And second derivative should be positive. Okay. So the second derivative test we won't do over here because it's very lengthy, but we'll just put the derivative equal to 0. So you can see that mu mg into mu cos theta minus sin theta upon cos theta plus mu sin theta whole square should be 0. So that tells you that mu cos theta minus sin theta should be 0. So zero point 0.4 into cos theta should be equal to sin theta, or theta should be tan inverse of zero point 0.4 or cot inverse of 2.5, whatever, that's the same thing. So that is the thing. Okay. And f theta, which will now have the minimum value, will be equal to mu mg upon cos theta plus, sorry, cos theta plus mu sin theta. So we'll have to calculate this theta. Okay, so on calculating this theta, you will get that theta is what we got above, 20.8 degrees. That, what was the theta we had got? Yeah, 21.8 degrees. So we'll get that same thing here. So this will become cos of that value, cos of 21.8 degrees plus 0.4 times sine of 21.80 steps. Okay, but you can also use a trick over here that if tan theta is zero point 0.4, or that is 2 by 5, then cos theta will become how much? So 2 5, this will be square root of 29. Okay, so cos theta will be 5 by root 29, and sin theta will be 2 by root 29. So this will become zero point 0.4 into 500 mu mg divided by this thing. So this thing is 5 by root 29 plus zero point 0.4 into 2 by root 29. This is 200 into square root of 29 divided by 5.8. So this is the minima of this function. And when you calculate this, you will get this as what we done earlier. Yeah, so you'll get the same value. You just have to do a bit of approximation. So 200 into approximately 5.39 divided by 5.8. So this will give you 185.7 approximately. But as you can see, a lot more effort over here because you're doing the differentiation, and that too I have not done the second derivative test. If you do the second derivative test to further prove that, so it becomes more lengthy. But it's easy to understand here that this is the minima only, this is not the maxima. No, minima is not average of local minima, beta. Minima to देखो, this is a periodic function na, because it involves sin theta and cos theta. So whatever is the local minima of the function only, that will be the global minima. If you have a polynomial function or something like that with a number of roots, then okay, there might be multiple local minimas and one of them will be the global minima like that. But this is not that type of function. So whatever is the local minima, that is the overall minimum of the function. Have you understood, beta Ayush? Hmm. Okay, because you can see this function is, it's like a constant upon a periodic function, and that periodic function is linear in sine and cos. So you don't have to worry about multiple points having local minima and which of them is the global minima. You just understand it's like a wave. The function's graph will be like a wave which will have an overall global minimum which is also a local minima point. Okay, so I'm not getting too much into the complexity of the mathematics in this because drawing the graph of the function and all that involves a lot of steps. Okay, it will take some time, and that's not required unnecessarily right now. What we just need to find out is the minimum value of f theta, So you can just understand that whenever the denominator is maximum, f theta is going to be minimum, and that's going to be in this situation. All right, so let us move on to more interesting problems involving friction now. So we will next discuss something called limiting friction condition. Okay? So, or limiting condition type of problems in friction. This was an example of limiting condition because we wanted to find out the limiting amount of force needed to move the block, that kind of situation. So let's move on with another example of the same. So now I have this situation once again. This is lying on a rough surface. Okay. But there are a few more things involved over here. There is a pulley, so one fixed pulley over here. Okay. So this is a rough surface which has coefficient of static friction, let's say 0.40, and coefficient of kinetic friction, let's say 0.35. Okay. And we have now got this kind of arrangement. So we got a second block and a system of pulleys. So another pulley over here attached to some kind of ceiling. We got this arrangement. Okay, now so this block is of mass m1 and this block is of mass m2. So given that m1 is equal to, let us say, 10 kilograms and g is equal to 10 meters per second square, find the minimum value of m2, so that if the system is released from rest with the thread taut, okay, then, or let's make the problem the other way around. Okay. Let's this time go for the maximum value of m2. Okay, so that when the system is released, then the blocks remain in equilibrium. So this is the limiting condition for remaining in equilibrium, not the limiting condition for motion to occur. It's just the opposite of what we've done in the previous problem. So then the blocks remain at rest in equilibrium. Okay. And second part, if m2 were instead equal to, let's say, 2.5 kg, okay, then find the accelerations of both blocks. Okay. So once again, very standard type of question. You will have to make use of certain things we've learned before, like the constraint relation for system of pulleys. But I'm sure all of you are experts in that by now. Okay. So work it out step by step. Kevin, you're giving the answer for the first part. उससे थोड़ा सा ज़्यादा होगा. The answer you given at that the system will be at rest, but you can increase the mass a little bit more also, because M1 is 10 kg, na? And coefficient of static friction is 0.4. So what is the maximum friction you have available? It is mu s into weight of M1. Okay. So you can see it will be a little bit more than that, the answer you given. So that's correct. Tension's maximum value, all of you have got this correct. All three of you sent me answers. Tension's maximum value is 40 newtons. So tension अगर 40 newtons है, इसका weight कितना होना चाहिए? 3 times that, ना? So 120 newtons. Correct, correct. So 12 kg is correct. Yeah, Kevin, 12 kg is correct. Yeah, I think I had made a calculation mistake, but 12 kg is correct answer. So the answer to the first part, the maximum value of this will go up to 12 kgs. And therefore, obviously you can see that acceleration will be zero. Sorry, second part, I don't want 12 kgs. I want more than that. So, I mean, I don't want 2.5 kg. I want 25 kg. Written 2.5 by mistake. Increase this to 25 kg. So you can see easily you can see the equilibrium condition here. For equilibrium on M1, this tension must be balanced by static friction. So this value we know is 100. And now the other block on the other side on M2, the total tension acting upward is 3T. Okay, and that is M2G. So if this one has zero acceleration, this one should also be in equilibrium. So 3T should be equal to M2G. Static friction should be equal to T. Okay, and the limiting condition now. So what is the limiting condition? For equilibrium, T should be less than equal to maximum value of static friction. So T should be, so this time instead of greater than, is less than equal to mu s into normal reaction. So T should be less than equal to mu s into M1G. So that means tension should be less than equal to 40 newtons. So tension is less than equal to 40 newtons. So our limiting condition is becoming this. So therefore M2G, which is 3T, should be less than equal to 3 into 40. Okay, so that means M2 should be less than equal to 12 kg. So the maximum force, the maximum value of M2 for equilibrium, okay, will just about be 12 kgs. As you reach 12 kg weight or mass of M2, your system will be ready to start acceleration. So you can go right up to 12, but not beyond that. Okay, Kevin, that seems correct. Okay. So now next part, obviously motion will start because we've bumped up the value of M2 beyond 12. We've taken it to 25. Okay. So that's where your constraint relation will become important. Okay. So remember the virtual power method, that is the easiest for constraint relation. So 3T acting on this one and T acting on this one. So accelerations will be in ratio for M1 and M2. The ratio of the accelerations will be 3 is to 1 because the tensions are 1 is to 3. Okay, yeah, I'll verify the answer. Just give me a moment. Okay, so this is moving with A1 and this is moving with A2. So at any point of time, you can see that M1 has an instantaneous velocity V1 with tension T acting on it, and M2 has an instantaneous velocity V2. So net power by tension, so that is plus TV1 minus 3TV2 should be equal to 0. So that means V1 should be equal to 3V2, which means A1 should be equal to 3A2. So this is your constraint relation. So now just to make things easier, what you can do is you can take A2 as A and therefore you can take A1 as 3A. Okay. Just makes life easier when you are solving these type of questions. Kinetic friction, so that is mu K M1G, because you know this normal reaction will be equal to this one's weight, M2G and T. So M2G minus 3T is equal to M2A2. That's your second equation, but we will write the second equation in this form. We'll incorporate the constraint relation already, so we'll write it as M2G minus 3T is equal to M2A. So 250 minus 3T is equal to 25A. This will be our form of the second equation. And finally, for M1, We'll have the equation. So this was the equation for M2. So for M1 we have the equation T minus kinetic friction is equal to M1 E1. So we'll write this as T minus 35 is equal to 10 into 3, or T minus 35 is equal to 30E. So this becomes our third equation. Okay. So now take this and this. 250 minus 3T is 25A. T minus 35 is 30A. Multiply this whole equation by 3 and add with this. So we have 250 minus, how much will this become? 90 plus 15. So that is 105. Okay. Is equal to 25 plus 90. So that's how much? 115 E. So we will get E as 145 by 115. Let's check my solving once. Okay, so A is that much. So that means my A1 will be 3 times this, 3A. So A1 is, how much will that become now? And A2 will be 29 by 23 meters per second. Okay, so I'll give you the approximate values in just a moment. So this is approximately 3.78 meters per second square, and one third of that. So this is approximately 1.26 meters per second. Yes, so that's correct. Okay. Everybody please check the calculations carefully. Okay. As far as I can tell, my final answers are correct. Just verify them once more. Equations are definitely correct. So yeah. Good. Okay, people, so hope this question is fully clear. Now, next example is again something where be little careful about deciding which direction in which motion will occur. So we have this kind of a situation. So this angle is 37 degrees. This is 90 degrees. Now we have combination of two blocks like this. So given that mass of block is 10 kilograms and coefficient of block friction, okay, this is coefficient of friction for block A with respect to the inclined surface. So this coefficient of friction is, let us say, 0.2, whereas mass of block B is 15 kg, okay, and the coefficient of friction of block B with respect to the inclined plane, that one, is 0.4, let's say, okay, and take G as 10 meters per second square. Okay, find the accelerations, if any, when the system is released with a thread taut like that. So why I'm saying this question is a bit complicated, because deciding the directions of friction, the directions of friction have to be determined from the tendency for slipping. So the first thing you have to understand, what is the tendency for slipping. Okay, so then you'll realize what friction is trying to do over here. So what is the so-called tendency for slipping? So suppose surfaces had been smooth. Okay, then B would slide down and A would slide up the inclined plane. Okay. You know this would have happened. Where this acceleration would have been this one's sine 53 component minus this one's sine 37 component divided by the sum of their masses. Okay. But anyway, so now with friction, what will happen is if friction is able to prevent, okay, we don't know whether friction is able to prevent slipping or not. Okay, but we know that if friction acts, this should be the direction opposite slipping. This should be the direction in which friction acts. Okay. So if friction is present, okay, whether it is kinetic or static, it is opposite to the acceleration for the smooth case. Okay. So that's why the direction should be like this. So once we know that, now what we can do is, okay, assuming slipping taking place. So both the frictions are kinetic. Yeah, if masses had been same, also the direction would have been same because 53 is a this thing, no, steeper slope. 53-degree slope is steeper. So same thing would have happened. Okay. So here let's examine all the forces. Yeah, I'll just give you the answers for the accelerations. Just give me a moment. Yeah. So on B, we would have 15 G sine 53 degrees. Okay. Because this angle would have been 53. I mean, this angle is 53 rather. Okay. 15 G cos 53 because mass of B is 15 kg. Okay. There is some normal reaction on it. There is tension T, and there is friction acting on B. So friction acting on B is coefficient of friction into normal reaction. So that is zero point 0.4 into 15g cos 53 degrees. So that will become zero point 0.4 into 150 into 3 by 5. So this will be 36 newtons. Okay, so this will be the friction on B. So for B, the equation for motion will become like this. Weight sign component minus friction minus tension is equal to 15E, or mass into acceleration. So this will become 120 minus 36 minus the unknown tension is 15E. This is our first equation. Okay. Now similarly for E, you can see the forces, they are, this was 10, right? The mass was 10 kg. Yeah, 10 and point 0.2. And on this, the friction's direction, as we have discussed, will be like this because it's moving in this direction. So this will be the friction acting on it. Okay. So normal reaction is 10g cos 37. So that is 80 newtons. So the friction acting on A is the coefficient of friction into that normal reaction. So 16 newtons of friction is acting. Okay. So for E, the equation of motion becomes T minus 10g sine 37 minus friction is equal to mass into acceleration. So that is T minus 60 minus 16 is equal to 10A, or T minus 76 is equal to 10A. This is our second equation. This is 156 minus T is equal to 50. Sorry, not 156, my mistake. Minus, so this is 84. Okay. So 84 minus T. Yeah. Okay. So now just add these two equations and you get the answer. Now the thing is, see, if supposing our assumption was wrong, कि acceleration नहीं हो रहा है, then we would have got A as a negative quantity from this, okay, and we would have had to adjust. Okay, but here as it is, our assumption is correct. So on adding the two equations, we can see we're getting an agreeable result that 84 minus 76 is equal to 25E. So the acceleration is coming out to be how much? 8 by 25 meters per second square, or that is 0.32 meters per second square. Okay, so is that correct, people? Yes, got the answer. Okay, but supposing, supposing we had taken some different values. If on the other hand, coefficient of friction for E was zero point 0.8 instead of zero point 0.2, then this second equation would have become, it would have become T minus 60 minus 64 is equal to 10A. Okay, so this would have become T minus 124 is equal to 10A. This is what the second equation would have become. So then in combination with the first equation, that 84 minus T is equal to 15A, this would have given us A as a negative quantity. So this would have been wrong. If A had come out to be negative, it would mean that no, the blocks are not moving. It would have implied that the blocks are at rest. Okay, and friction are static friction. So friction on A is less than mu A into Na. and friction on B would also be less than equal to mu B into NB, such that acceleration would be zero for this. Acceleration would be zero for this. So that is the thing, ना बेटा. Negative acceleration मतलब opposite direction नहीं होगा, because क्या हो रहा है ना, it means that if we apply the full friction in the direction that I have shown, the friction is actually creating motion, no? Friction is generating the motion. So that means we have sufficient friction to prevent the motion. You understanding the point, beta? Acceleration coming out negative here doesn't mean that actually the motion would be in the opposite direction, because हमें पता है कि friction ही नहीं होता अगर, then the direction of slipping would have been the way I've taken, ना, he is going up and not down. So that means if instead I'm saying that no, he is going down, that means I'm saying friction is creating that motion. Now that's against the nature of friction. No? Friction prevents motion, it does not create motion. So I can be sure that if A is coming out negative in my equation, it means that actually there is no A. And actually there is static friction less than the values that we've taken here, and that is preventing the motion from taking place. Okay, that is the only correct conclusion in that case. Okay, so this is a very key problem, that make sure that you revise this question carefully today before you start working out more questions and things. And after today's lecture, you should be able to complete HC Verma fully. Okay, so keep that as a target for the next time. If you haven't done HC Verma fully yet, then friction chapter of HC Verma. Okay. Now next question, equally important. Now we come to the more interesting situation of I mean two block problems. Okay. You will eventually see three block problems also. Okay. Now just to make the first version of this simpler, we will take the ground as smooth. Okay, of course, there can be a situation where the ground is also rough, but this surface, it has a coefficient of friction of, let us say, 0.4. Our acceleration due to gravity is 10 meters per second square. M1 is, let us say, 5 kilograms, and M2 is, let us say, 15 kilograms, three times that. Okay. And the system is at rest initially, but we apply a force horizontally on M2 to make it start moving. Okay. So the system is at rest initially, okay, and horizontal force F is applied, okay, as shown. Okay. Now we have to find their accelerations. If in the first case the force we are applying is, let us say, this one. Yeah, the force we are applying is, let us say, 60 newtons. Okay. And in the second case, the force we are applying, instead of 60, the force is 100 newtons. Let's see what happens in this case. Okay. Okay, Snikita, I'll show you the question in the end. Let's move on to this question for the moment. Okay. So now see here, what is very important is that the moment we apply this force on M2, M2 has a tendency to move along positive x direction. If I take this as my x-axis. Okay. So क्या होगा? Therefore, as far as M1 is concerned, M1 is sitting on M2, okay, and we are applying this force on M2. So with respect to M2, if you were sitting on M2, what is the tendency of M1? It has a tendency of slipping backwards. Okay. So therefore, in M2's frame, M1 tends to slip back, okay, negative direction. So therefore, what is the direction of friction that will act on M1? It's in the forward direction. So therefore, friction acts along positive x direction on M1. Okay, and vice versa for M2. So M2 be equal and opposite reaction friction ऐसा act करेगा. Okay, so this is the direction in which frictions will act. Okay, so that's the first thing you have to understand. Then the other thing you have to understand here is that what is friction trying to do? It is not trying to keep the blocks at rest, because that it cannot do. Na? The surface below is smooth. Okay, so if there is sufficient friction to prevent slipping, okay, then M1 and M2 move together, okay, with common acceleration, ALS. Okay, and on the other hand, if friction is unable to prevent slipping between them, okay, then what will happen? M1 accelerates at E1, M2 accelerates at E2, where E2 will be greater than E1. The one that you're pushing, the one below, it will slide faster. And obviously, eventually M1 will topple over. Okay. So this is the thing that you have to understand. Okay. So yes, many of you got the answers correct. So what you will see when you solve this is in the A part, what happens is that no slipping occurs. So they have common acceleration, and that common acceleration will come out to be 3 meters per second square. Okay. And the friction acting will be static friction, and that will come out to be 15 newtons, even though the maximum friction available to us is more than that. The maximum friction available to us is 20 newtons, but only 15 newtons will be acting. Whereas in the second case, we will see that there is slipping. Okay. And E2 will work out to be, what is it, ET by 15. Something like 5.33 meters per second square. And E1 will be 4 meters per second square. And the friction will be kinetic friction, and it will be equal to 20 newtons. So I'll show you how to get these results, but those of you who already worked it out, you can verify your answers. Yes, Kevin, your answers are correct. Naman, your answers look to be correct. Yes. Second part you have to check. First part is correct. Okay. So the whole question is, see, I have to understand which of these two cases is going to occur. Is it going to be the no slipping case? Okay. This is the no slipping case, the first one that I've shown here. This one is a no slipping case. Is this going to occur? Or on the other hand, is this going to occur? The second case which I'm circling now, where E2 will be more than E1 because we don't have enough friction to prevent slipping. So I'll tell you, there is a sort of logical method of working out this thing, that which of the two things is occurring. And that logical method is very simple. It is like this, that it's based on free body diagram concept only. If you look at the free body diagram of M1 and M2 separately, it doesn't matter whether there's slipping occurring or not. Okay. This way there are two forces acting horizontally, or is where there is only one force acting horizontally. Of course, there are vertical forces. So they are like this normal reaction here, weight here, some normal reaction from the ground. Okay, but okay. So the thing is that this guy's acceleration and this guy's acceleration, both of the FBDs I'm making in ground frame. Okay, I'm not getting into any non-inertial frame here. Okay. So this FBD is also in inertial frame. This FBD is also in inertial frame. So you can see that M1 E1 is dependent on friction. Okay, and on the other hand, this guy's acceleration can be controlled with the amount of force, irrespective of whether they're slipping or not. So therefore, you can see that from equation 1, you can see that E1's maximum possible value is friction's maximum possible value divided by M1. So you can see that E1 cannot go faster than this much, 4 meters per second square. So this is something very important to understand, that no matter how much force you apply from below, you cannot make the upper block move faster than 4 meters per second square. So that means if you want no slipping, you have to give the system a common acceleration of less than 4. Okay. So therefore, from this you understand that if the blocks move together, okay, common acceleration, then that common acceleration should be less than equal to 4 meters per second square. And therefore the amount of force we are applying should be less than equal to m1 plus m2 into this maximum acceleration. So it should be less than equal to 5 plus 15 into 4. Okay, so that's how much. It should be less than equal to 80 newtons. Okay, that is the condition for no slipping. Okay, this is the condition for no slipping. Okay, and on the other hand, if F becomes greater than 80 newtons, okay, that means the friction acting will become kinetic friction, which will be mu m1g. Okay, and E1 will be mu m1g divided by m1. So E1 will be 4 meters per second square, whereas E2 will become greater than 4 meters per second square because E2 is going to be F minus kinetic friction divided by m2. You can see because your F is greater than 80 newtons, this is going to be greater than 4 meters per second square. Immediately you can understand this. Okay, so this becomes the condition for slipping. Okay. Now if you apply this over here in this question, you can very easily understand what is happening in each of the cases. The first case, you can see that I'm applying a force of only 60 newtons, so I'm satisfying the condition for no slipping. That is the priority, that is what friction wants to do. Okay. So you can see that for first part, F equal to 60 newtons, A1 is equal to A2 equal to A. Okay, common expression. Okay. And you can just make a combined free body diagram. So that friction is an internal force, that static friction. So you can see this A is F upon M1 plus M2, which will come out to be 3 meters per second square. Okay. And then you can make an FBD for just M1 to understand how much friction is acting. Now, the static friction acting on this, but how much that static friction is. You can see that static friction is 5 into 3. Okay, that is M1A, that is 15 newtons. So you can see a static friction of less than the limiting value is acting. Okay. And likewise, you can understand in the FBD of M2, there is F is the same static friction. So F minus static friction is M2A. So that is going to work out because you substitute the value of F as 60 and the value of static friction is 15. You get the same value of acceleration. Yeah, then it's I'll scroll up. Okay. So now second case, immediately you can see what is happening. When we are putting the force of 100 newtons, there will be slipping. Okay. And the friction acting will be kinetic friction, which will be mu m1g. So that was how much? That was 0.4 into 50. So 20 newtons of kinetic friction will be acting. So M1's free body diagram will have kinetic friction of 20 newtons, giving it an acceleration A1. So A1 will come out to be 4 meters per second square. Whereas M2's free body diagram, you are applying the external force of 100, but the kinetic friction is 20. So it will have a different acceleration, A2. Okay. And F minus kinetic friction will become M2A2. So 100 minus 20 will become 15A2. So the acceleration of this guy will become 80 by 15 or 5.33 meters per second. So as expected, A1 is going at its maximum possible value of 4, but A2 has become faster than that because we are applying too much force. So M1 is not able to keep up with it because there isn't enough friction between them. So the slipping starts to occur. Okay, so this is a critical trick of solving this type of problem. We'll see many more cases of this in the next lecture also. And like instead of applying the force on the lower block, you can apply it on the upper block. And there might be friction between the ground and the lower block also. And these different type of cases. There are few of the questions of this type in H.C. Verma's exercise also, including a 3-block problem where there are 3 blocks kept one on top of the other instead of 2. So you can apply similar methods and start working out all this. Okay, you are now within reach of finishing HC Verma completely. So that should be your first target as far as your own assignments is concerned. And then of course continue with the exercises from the module also. So next lecture we will discuss some selected questions from HCV and some module questions plus some questions of my own. Theory wise we are done with friction now completely. So that's it for today's session, people. Wish you all the best.